In this video, I will talk about the exact thought process on how to predict an outcome based on the sequence of inputs, and I will walk you through the code to exactly implement it. To be more specific, the problem is that we are given a sequence of events, which in this case is the interaction log of different users that are working with a quiz. The events can be changing the answer or requesting hint or using the different tools, and then without knowing what was the correct answer to each question, we want to somehow predict that based on this sequence and this trend, can we predict their final grades. So without further ado, let's jump right into it. Welcome everyone to your channel AI Fun Fact for All. For those of you who are new to this channel, my name is Pedram Agan. I'm a PhD student in computer science with extensive knowledge in AI and machine learning and teaching. And in this YouTube channel, we strictly talk about AI tools and its advancement in a simplified way that we can use it in our everyday life. So in this video, I want to talk about one of the projects that I recently worked on, and I want to walk you through the different thought process and give you some insight on how you can actually implement your code. So I will walk you through the code. It might seem to be a little bit daunting, so you can basically just try to digest the whole idea rather than going into too deep. And if you are familiar with some coding, then this is the best one for you. I will also put the link of the project GitHub in the description of the video, so you can check it out later. Before we actually go into the code, let's reiterate the problem and try to break down the concepts that what we are actually trying to solve. As I said earlier, we have a sequence of events that are irregular in time, which means that there is no exact time that they are going to happen, and their duration can also vary. So what we have is the log of the user's interaction. As they go into the website and try to answer the different questions, we will log some information, such as, for example, the time that they changed their answer, or the first submitted their answer, or they requested for some hints, or they interact with some of the tools that we make available there, such as the Streamlit, or for example other tools such as the ChatGPT API. So we extracted and have those information in event format, and we also have the exact time that those logs happen. What we really want, we want to know, without us knowing that which answers each individual choose, but just knowing that they change their answer or submit this answer, or how long this interaction take, and try to predict without knowing what is even the question and what is even the exact solution. We want to predict what would be their grades. So this is basically a hard problem and can be considered as a sequence to a prediction problem. So we have a sequence of different events, or we can call it mode, and then we are trying to predict the output. One of the ways to solve this problem is to use HMM, or hidden Markov models. HMMs are powerful in order to detect different hidden modes inside the system and try to somehow find the relation between them in a sequential manner, and then try to predict that given this sequence, what is going to be our next mode. So HMM are very powerful when you don't know what is your individual mode and you try to somehow extract it from your data. However, in our case, we already know what are the important modes, and we consider there is not much of other basically modes or events that we didn't log. So basically we already have access to all of it. So one way we can use to solve it is basically using the transformer architecture. So if you already know, every advancement that we have right now in terms of ChatGPT or any other large language models is the backbone is going to be the transformer, which is basically using an attention mechanism and try to find the relationship in between, for example, the individual tokens using the self-attention or cost-attention, and try to find their relationship in a long context format. Even though that our context is not long, but finding the exact relation between each individual events can be a complex task, so that's why we suggested to use a transformer architecture. But there's also something that we need to pay attention to, which is the transformer architectures are basically data hungry, which means that they require a lot of data in order to be fully trained. However, for our case, we don't have enough data. We just have, for example, like 60 to 100 different users, and we'll log about, for example, 3 different questions that has around like 20 questions each of them. So roughly speaking, we have around like 250 to 300 total data, which is actually not large enough. So we will see in this project how we can try to solve this issue of not having enough data, and this is actually a very critical problem in many cases, that we don't have enough data, and how we can actually try to use some approaches such as self-supervised in order to generate some other samples that are kind of similar. So we will see that what is the contrastive loss and how we can use that in order to pseudo generating some data in a data augmentation phase. The next question that is going to be brought up is that, are we going to use a transformer architecture from scratch, or are we using something that is already pre-trained and we try to just do a little bit of fine-tuning? So if we want to build up a whole transformer from scratch, regardless of the size of the parameters, we require massive amount of data, and also we require a lot of training time and a lot of like iteration to actually fully train these models. And it was shown that these models can be easily overfit and kind of like you try to find the results that are not even good compared to an LSTM or HMM models. So if you don't have enough data, if you don't have the capacity to train these models, I don't suggest that route. But there's also another way which you can use from an already pre-trained model, which we can call them a foundational model. So let's talk about foundational model. If you have a model that was pre-trained on some general task, you can consider this model to have some useful information which can be used later on in different downstream tasks. So let's say I have a model that was trained on some unlabeled, unsupervised task, which is just, for example, trying to find in an NLP task, we can consider, for example, predicting different tokens, and we try to randomly pick some of the samples of words, and it try to predict what is that masked token. So this is called like reconstruction. We can do the same with constructive, which we basically try to find a different views of the same token and try to somehow create a larger distance between the tokens that are far from each other semantically, and close the ones that are make them closer to each other, the ones that are semantically related. These ideas of pretext, or basically any pre-trained approaches, which is not just for NLP tasks, we also have it for example, vision task, for example, an ImageNet that is trained on massive image dataset, and then later on I can use it for different downstream tasks, such as, for example, face recognition, or for example for authentication, or for example for anomaly detection, and so many other downstream tasks. So what these models will try to learn is some representation learning. So they try to obtain some knowledge from the input data that can be later on be useful for the downstream task and can make the whole process a lot easier for us. The whole concept of ChatGPT or any other models that are very powerful right now is this, because they are trained originally on a massive amount of data, completely unsupervised. So they just try to learn how the for example sentence work, how different words are connected to each other, and then after that they will try to, for example, instruct unit and for example RLHF, which try to align it with the human preference. So basically this process of doing an unsupervised or self-supervised in the beginning and then convert it in a transfer learning to some downstream task is very popular method. So that's why what we are trying to choose as well. Now let's jump into the code. I will walk you through different steps of what we have implemented, and we'll try to talk about the reasoning behind why we are doing that. And I also talk about some of the tips and tricks for the implementation and how you can actually use it on your own project. The first thing I want to talk about is that right now I'm on my Mac, but this sort of fine-tuning or basically training these language models are kind of resource extensive. So I don't think my laptop would be able to have enough resources to actually do this task. And also I don't have a GPU, which is the accelerator for running this task faster. So that's why I'm going to connect to my computer lab and then I will try to run it from there. Since I'm using the VS Code, there is an option to connect to the host to your computer in your remote, so that's why I'm trying to use the VS Code in its SSH basically format and try to connect there as if I'm in my lab. So how it works is that there might be some situation that you might need to have a tunnel in order to connect. So for example, there wouldn't be any direct SSH so for some security reason. So if that's the case, I will tell you how you can manage that as well. And if it is not, you just simply will do the SSH and try to select your, for example, computer instance or OS format in VS Code, and then after that you will easily connect it. So what you need to do in order to create some information about your SSH configuration, if you are in Mac, you can do it inside your vim in .ssh config. So inside this, as you can see, I have created on the very top, I have created the first host, which I call it Uni. So this is just a name, it's not important. You have a host name, which is basically the one that you are going to connect to, and then you are going to define the port and then your username, basically what is it. And then I also created another host, which is the lab, but this one cannot be directly accessed, so I first need to connect to this Uni proxy, and then after that jump to the lab. So that's why for this one I'm going to use the host name specific for my lab, and then I'm going to choose the port. As you can see, the port can be also different, username, and then I'm going to choose the proxy jump to be the Uni. So every time that I write connection SSH to a lab, it will first connect to Uni because there's a proxy jump, and then after that automatically convert to a lab. Awesome. So let's go out you can definitely try it in here as well, and then you can see that okay, it is actually working. It might, if each of your nodes have different passwords, it will ask you different times. What we need to do now is that we go to our VS Code. There is this option on the bottom that is asking you to open a remote window. If it is your first time, it's gonna ask you to install an extension. Go ahead and do that, and then it's gonna ask you to you're gonna choose the connect to host, and then if you have already defined it inside your SSH config, it will come in here. So I'm gonna choose the lab. It will open up a new one, and it will ask me to input my password twice. Perfect. Now that we have access to our lab computer, we can go ahead and run without being worried about the resources not available. If you don't have access to that, you can basically do it with your Google Lab or any other instances. For example, Compute Canada if you're in Canada, or AWS or other instances with Microsoft like Azure and so on. What we need to do first is that to import some of the packages, OS, Seaborn and Matplotlib, not very complicated things, and then here I will get my current working directory. Why this is important? Because sometimes you are working on some directory and you are trying to import something that are not in your main directory that you are in, such as right now I'm in AI tutor sequence modeling, but this one is inside the sequence modeling folder. So if I want to access to some data, I need to make sure that I'm aware of this. If you want to change your directory, what you can do, you can get your current working directory and try to do whatever approaches you want. So for example, in here I try to go one step back, one folder back, and then try to choose the change directory, so then later on my directory would be the one that have access to all of it, because I will require access to my data folder while I'm inside a child folder. As you can see, we have some index, we have a username, which right now all of it is A1, but then we also have A2 and so on. Then we have a date time format, we have time session, and then we have the space, which is the different problems that they're trying to solve, and then the specific actions that they want to do. And then we also have a separate one for the second group, where we do the same with it, and then we have another thing for the score, which is basically their actual human validated grade. So I can actually go ahead and run this too as well, so we have access to everything. So in here I just concatenated these two data frames, so this includes A1 and also the group 2. In here I am running the basic score. So as you can see, how it's writing is that it has the different usernames and it has the score for different problems. So we have 3 problems for each of the users, and then we have around 50 for group B and around 50 again for group A, and 3 different questions, so around 300 samples, but not all of them are actually completed, so we have around like 250. So now what I'm trying to do in here is that I don't want it to be like this, so that's why I stack it and then have an individual score which has the score for each individual problem. So I will have the problem as a separate basically column, and then the score will include the score for each individual username. Here, this is just to keep track of the original data frame if we later on change it. Now this is important because we want to know what are the unique actions. So these are the different modes that we have, and as we mentioned, there is no direct relation between them, and there is no reason on when each of them can happen. So they are very irregular, and as you can see, the number of them are actually kind of like different. We have change answer, which basically changing the answer to a question, which happened 11,000 times, and then we have something like around 9 times user logout or the stop reading. So we see that a lot of the actions that are captured in here might not be very useful in order to predict the output results. One of them is, for example, user logout, or for example user login, or for example autosave or load default. So these things are not necessarily important, so that's why we try to remove them. And then we have this set of different actions, including like completing submodule, user request, run code, request first hint, streamlit interaction. So different set of logs, and then as you can see, the number of them are actually also very different, and when they happen is also very much different. Then after that, we have the different space with the value count. We have the problem tree that's around 10,000 score. For the problem 2 we have around the same, and then for problem 1 it is less. And then we have other things, which is the AI chatbot, code editor, and EDA toolbox. We have some different sub modules that we also try to extract log from them. We don't want that. We want to consider the information or the logs that are just specific to the main platform. So it's kind of like also disregard them and just have the information from the space 1, 2, and 3, which is related to problem 1, problem 2, and problem 3. There is another data pre-processing steps in here, which is some of our data points in the date and time might not be in a date-time format, so we try to take care of that in here. So now here is the critical point. What we are trying to do is that we have found a list of different actions, and that's what we're going to use as our modes, and then we try to predict the basic score. So that is basically what we are trying to do. And as we mentioned in earlier, what we want to do is that we want to try to solve it in a form of a sequence learning, which means that we have a sequence of this data, which in here are our different tokens, and then we are trying to predict that, okay, if that's the case, what's going to happen after that, and we are hoping that that thing at the end is going to be corresponding to their score. Okay, we try to convert these actions to some unique tokens. So this is arguably one of the things that there are different opinion about it. So it's very controversial. Some people say that having the same basically actions in its most natural language format can actually help this LLM to better understand it. So let's say if I have a change answer and I give it to this for example foundational model, it understands that, okay, so this is the change answer, and then maybe I'm trying to do the same, maybe I'm trying to predict the action, and I'm trying to find the result. So change answer is more related compared to, for example, a user request or so on, because RC doesn't necessarily mean anything to a natural language model. So this is actually true if you want to consider a LLM. So if you have a large language model and we want to do either an in-context learning or try to do fine-tuning, since these are large language models and they actually have the capacity to understand and increase their generalizability to understand that, okay, this change answer can actually correspond to a value of of our score, and then I can actually provide a descriptive for the instruction that, okay, these are the task and these are the sequence. Now this is what I want to do. So I can also provide the instruct. I would say that, okay, that's a better option. But right now we don't want to use a large language model. We want to use basically a pre-trained, a smaller model. The main reason was that we don't want to use any sort of API or any local LLMs, and we just want to train a transformer model, and we didn't want to do it from completely scratch. So we tried to use something like a BERT or DistillBERT, as we will get into that. For those model, I would argue that having a complete name of it wouldn't help a lot in terms of understanding and finding the classification problem, because the task that we are doing would be considered as a category of regression or classification given a sequence of input. But then there might be another argument to this that's going to say that, okay, if you are changing your actions into something that are completely irrelevant, how do you justify the fact that a pre-trained model can actually help you to understand the next token or get some useful information? How do you know that this unsupervised learning was actually helpful for your downstream task? So this is another critical and very controversial question. So I would say, even though that these tokens, the ones that have like UA, FAR, does not necessarily have any natural language meaning, and there is no semantic relation between them, and our pre-train never actually saw any of this, and you will see in a little bit that we try to even extend our tokens, so we basically kind of throw out whatever tokens or embedding that they learned before, and we try to extend it. But again, there are some basically knowledge higher in their attention layers and cross attention and self-attention that are still useful. So even though that maybe the embedding layer or the tokenization are not useful, but the other layers are still going to be useful and will help us a lot to better understand this and find the answer to this. So for that specific reasons, we try to convert them. And another important thing is that since these tokens are smaller, their representation or the token in their embedding size would be smaller rather than, for example, a change answer which might require to have at least like 2 or maybe in some cases 3 or 4 tokens. We just can do it in one. As you can see in here, I have created this, which are basically the timestamp, the problem, and then the corresponding action right now, which are these unique basically actions. What we really need to think about right now is that the absolute value of the time does not really matter. What's really important is how long did it take to actually do this specific action, right? So what we're really interested in is the action and then the duration that it took until before the next one. So how long was the thought process in actually to do this task? So that's why we create a new feature called the duration. So for duration, what we will do is that we subtract the 2 consecutive time step and try to come up with some value. There are some non-values which we later on try to solve it by replacing with 0, or if it is larger than some number, we just put another value because that's not what we are interested in. So here is the updated result. We have the duration for each of the specific action for each of the individual user. And if you look at our database data set right now, we see that our mean value is 0, our max value is 1198, and then we have the mean of 19 seconds, and then the standard deviation of 47. So that's not bad. What we want to do later is that these different time steps does not necessarily mean something important, and same as how we didn't want to have multiple tokens for each individual time, we also didn't want to have multiple basically different times, because for example 21 second and 20 second are not different that much. So that's why we are trying to find some beans that basically put the different data points in that region inside that bean, and then use that bean as a new token associated with this specific action. So and we call it after that. So we create this decoding for us, and then we convert it based on some different time. For example, T0, T1 all the way to T max, based on how long would it take, and we already know that how the distribution is going. So we try to make it somehow that it makes sense, and we have a good distribution of different time frames. So right now the duration are actually also tokenized, are actually kind of like embedded, and or basically better say it's not embedded, it's actually encoded, and then later on I can embed it because there's not a lot of this different encoding, so it makes sense to actually find the new tokens for each of them. But what we need to do right now is actually to create the sequence. So the sequence needs to be created as a combination, as different like for example combination of actions and the associate, for example, time, and then again the next action, the associated time, the next action, associated time, and so on. And then we also know that we have 3 different problems, so I want each of these sequence to start with a problem. So for example Q1, Q2, Q3, and then after that the end would be basically my score, or what is the actual value. So this is something that we are interested in. So this code is actually try to do that, and in order to make sure that our sequence or these steps that we are creating are actually unique, we will create them in a dictionary format, that the keys are actually a tuple of the user and the problem. So if you have a user and then problem 1, problem 2, problem 3, then it is unique, right? And the next there's no other data that have the same thing. So what we will do is that if the data was already there, we will just extend it. So we will add it to the previous key, and if it was not there, we just create it, and as we said, we start with a Q. So Q the problem number, and then after that the different actions. So we see in here that we have the number of sequence to be 254, but we have the number of scores to be 267. So this is a little bit odd because the number of sequence and the scores should be equal. So what we will do right now, we will try to see that what are some scores that we have which there isn't any equivalent score for them, and that's why we have those dictionaries. So right now I can easily pair them with the corresponding value. So right now I have my sequence and the score length to be exactly similar, because if there was any score that there wasn't any corresponding sequence for it, I actually eliminate it. So in here we created the score list, and from this part I am trying to train the model. So let's take a look at what we have included in here. We have included the torch, for the training, and then data loader, data set, and random split. These are the ones that handle accessing data when we are doing the training. So data loader will kind of like pack the data and make it ready for the GPU based on the different calls that we give it, and then it will create the batch size of data, and then pass it to the model to actually implement the result. And then we have the transformers, which is from the Hugging Face for our model. As we said, we want to have the BERT. We have two things. We have BERT tokenizer and BERT for sequence classification. So the BERT tokenizer is the one that is responsible to convert our actions to a specific tokens, which is basically the text converted to some vectors, and then BERT for sequence classification is since our task is a classification, because we want to predict just one number at the end, we will use this, and we use the pre-trained model, so we have access to the data, and we also get the Adam W and then the schedule with warm up as another library in here. So a schedule with warm-up is very helpful, because in the very beginning we don't have a lot of useful information, so that's why we want to do a little bit of warm-up for our learning aid, and after that we want to try to, for example, decrease our learning. In the very beginning, our learning rate is our value that we have is not very true, so it is not very much makes sense to actually change the weights so fast. And so that's why we have a warm-up phase, and then after that we will go and try to continue. We have VanDB. So VanDB is very helpful when we want to track our results. So we have this VanDB, and then when I'm doing the training, I can go online and check that how the result is going so far. So for VanDB, if you are in education, it is accessible for free, and if you're not, so you have to pay, but it's not a lot, but it's actually very good, useful information that you don't necessarily have to have your result locally. So you can run your desktop somewhere and then just look at the result that you're getting on your phone or anywhere that have access to the internet. So for that reason, this is very helpful. I have created this project and the Mars app. For this one, I'm going to use the BERT on case. I will be going to use the BERT tokenizer to basically use the tokenizer from the pre-train, and then also our model again from the pre-train, and I put the number of labels equals to 1 because I want to have only one prediction. So what we need to do right now is the fact that the tokens that we have added are some special tokens, and it doesn't necessarily have the BERT vocabulary doesn't necessarily have them. So what we need to do right now is to add these new tokens, and this is actually kind of the main point of this project, because we didn't want to have some embedding from before that kind of like get into the place of conflicting with the new tokens that we have. So how it works is that right now, let's assume we have the same previous embedding, and right now I added a small embedding at the very end. So any of the tokens that I have right now will come through this embedding. I'm not using any of the previous pre-trained embedding. It will go in here, but then after that it will go and populate through the other high level of my network. So I added this, and then I also resized the token embedding based on my new vocabulary size. So as you can see, right now it has around 30,000 number of embedding. And then I need to create a dataset class. So the dataset, as we mentioned, is required by the model. Each time it requires some init instance, which actually provide any related information or any property that we want to define. It requires a length, which actually return the sequence, and then another important one, which is get item, which is each time when we are trying to run the data loader and specify the batch, it will call this get item. So what you need to do in here is that you need to return what the model is looking for. So I have previously created the score, and I have created the sequence and a score. So what I will do right now is just I will create a tokenizer with encode plus. So I will do encode plus because I don't want to add the different encoding steps separately. So encode plus is nice because it has everything inside it. So I will pass the sequence to it, and then I will add a special tokens, which is like CLS or SEP. It will automatically add those. So those are important because these models will learn that, okay, this is the end of token, and after that whatever we have is like pad or whatever we have are not meaningful for the model. So these are special tokens that are very important, so it will automatically add it for me. We can define a maximum length based on my sequence. I already know that what is my maximum length, so I'm not gonna go beyond that. So there wouldn't be basically any truncation, but I just put the truncation goes through just in case. We put a maximum length for padding, so from the end of my sequence until how much my sequence length size is, we will put padding, and then our return token will be PyTorch compatible, and we have the attention mask equals to true, which is important in some cases that during the training, if I want to do for example sequence to sequence learning, it might be helpful. And then at the end I will return a dictionary. So dictionary includes the input ID, attention mask, and label. So this is very conventional of the transformer models. So they require transformer models in terms of NLP or any LLMs. So they require the input ID, which is basically the sequence, the ID of the sequence, and then we have the attention mask. So if there is an attention mask, we need to put it in, and then the label also basically my score. So I will return that, and then here we have my device. And so as you can see right now, I have access to the CUDA in my lab computer to basically be able to run this task efficiently. And then what I need to do, I need to convert both my model and my data to my GPU, but the whole data doesn't need to go there, only the batch sizes. So that's why we have this next step, which is basically it's called the data set. So it created the data set for us, so the instance is ready right now. And then in order to create the reproducibility, I put all of these different things. All of them are actually needed. So we have the torch manual seed, but then we also need to do CUDA. So this is important because I see a lot of people do this manual seed for torch, and they say, oh, we don't get the same result. The reason is because you are not doing in the CPU, and the manual seed for the GPU is different. So that's why you need to have a manual seed for basically torch and the CUDA and separately. And then you will generate, you can define or specify your generator based on this manual seed. So what are the different steps of basically randomness? It is one of them in the train test split. So the random split requires that, so that's why I put the generator equal to G. And then here we can see the data loader, which I was talking about. So we have we pass the train data set, the portion, the 70%, or in this case 80% of the data set, which is only used for the training, and then 20% untouched just for testing later down the road. I choose the batch size equals to 8. We put the shuffle equals to true, and collect function we don't have any. So worker and the generator. So worker, if you have multiple worker you can put, but right now we just put the seed, and then we do the same for my validation. So if I look at my length of data set is 256. I will choose the number of epochs to be equals to 50. I will use the Adam for my optimizer, you give the number of parameters, and then you have some learning. So this is basically your hyperparameter. So the people that try to come up with the better result, that's where they try to tweak. So it's kind of like very time consuming and extensive process. You need to go over different values to come up which one is the best and give you the best result. And then I also need to create a scheduler. So the scheduler, what it will do is it will give the optimizer and also the number of warm-up steps. For example, in this case, I'm saying 4 steps, 4 original steps. We want it to be warm-up, and then I will also put the total number of steps to it. So later on, when I'm doing the training, it will be considered. Then I will create some function for my training loop, which later on I will just try to call it. So what it has is that it has the model in its train mode, so model.train, and then we started the loss from 0, and then we're gonna say, okay, for batch in our train dataset, because we are going to convert it into batch size of 8, and then I'm going to create this batch with this key and value. So if you remember, we return the input ID and then the mask and then the scores in a keyword format. So what we need to do in here is that we need to move our batch of data to also the device as well. So our SQ is 1, which basically means that I try to shrink it, so we don't have extra dimension. This is for dimension, and then I just convert it to my device. And since it is a dictionary, I need to have 2 stars and pass it to my model. And my model, as I mentioned, requires data specific format. Then we have my loss function, so output.loss, and then add my loss to my total loss, the optimizer.0 grad, because now the gradient is finished. The next step is need to start fresh, and then loss backward, and then we do our gradient clipping in here, and then goes optimizer step, and then a scheduler dot step. So we have an average train loss, which is basically the total loss divided by what is your train data loader. And in here I basically want to update my VanDB, so we'll look at the VanDB as well. After this basically whole training is done, I will also do my validation. So I will convert the model into evaluation mode and start the validation from 0, and basically try to do the same. The only thing is that I don't have my gradient, and whenever I do the model.eval, it automatically set the gradient, doesn't have the gradient, but I also don't put the gradient step as so after that I have this average validation, and then update the VanDB loss as well. And I also want to plot show the result or print the result every 5 epoch as well. So let's actually run this and see what we can get. So it will try to print it every of 5 epochs. So right now we see that the epoch 1 is finished, and we have this result for the training loss and my validation loss. So as you can see, even though that this is running on GPU, it's going to take a little bit of a while. So right now we are going 6 epochs, and right now the 11 epochs finished, and now I can go back and look at the results in the VanDB, and I can see the results in real time in here. So the dotted line is basically the validation loss, and this one is actually the train loss. So I can see that this is how the training loss is changing over time for different steps, or basically different epochs. After around 4 minutes, the training is finished, and then if you go back to the VanDB, we can see the validation. So the validation is kind of steady after a while, and then here we can see our training loss. The training loss is still going down, so maybe we can even extend the number of epochs. Now let's take a look at some of the the result or evaluation in here. So here the first one is basically our confusion matrix. So what we really want, we want to have the maximum number of elements on the diagonal, and here are the misclassified elements. As you can see, we have a lot of misclassified values. So this is the vanilla bird case. So it is showing that we cannot necessarily get the best result. So here's the maximum prediction, minimum prediction, and then here is basically the which of the sequence are the worst prediction, which of them are the best prediction, and then here is the errors. So as you can see, these are the blue ones are the actual value, and the red are actually the error bar, and this is the final result. So we can see that our MSP is around here, and our R2-score around here, and the maximum error around 612. So this is not the best result that we get from the vanilla version. In the next video, part 2, I will try to go over what are the different updates that we can do in order to make our results better. So stay tuned for that, which we go over different methods such as curriculum learning, QLoRa, and basically the data augmentation for the self-supervised method. So there are so much to learn in the next video. This is the GitHub page, and then if you come to the sequential model, this is the Jupyter file that I was working on, so you can work it yourself and try to see what results we can get. Thanks for watching until the end of the video. If you want to get more information and try to get involved to become an AI engineer in this area that AI is booming, make sure to watch this video that I created before, that I talk about the step-by-step ways how you can become an AI engineer, and what are the courses that you can take. If you enjoyed the video, make sure to like the video, and more importantly, subscribe to the channel so you get more information, and let me know in the comments what do you want me to talk about next. Thank you, and see you until the next part.